Hello. So years ago, when I started studying computer science, my friends and I spent a lot of time learning new programming languages just to instruct computers so that they do what we want them to do. And I always thought to myself, why is it that we have to learn a new language as opposed to computers learning our own? Since then, we've come a long way in making machines understand natural language. Just this morning, I received a thank you note by email from a friend, and immediately I was suggested some answers. You're welcome, no problem. As if the machine read my email, understood it, and was ready to respond to it. More recently, ChatGPT has taken the world by storm by receiving our questions and answering our questions all in natural language. But how did we come this far in making machines understand natural language so well? The first question we need to ask is, why was it so difficult in the first place? Well, natural languages have a very large and open vocabulary. In addition, they have complex syntactic structures, but most importantly, they are often not clear. The interpretation of words and sentences may be different depending on the context. For example, if I tell you, the professor sent the student to see the principal because he was talking in class. Who's the he? The student. Same sentence, but different ending. The professor sent the student to see the principal because he wanted to see him. Who's the he? The principal. We, as humans, we know that. We can figure it out because we understand the concept, the context, and we have our knowledge of the world. And that is what is very difficult to do by computers. Yet, in the past few years, we have seen some fantastic advances in how computers process natural language. So how do they do that? Well, research to make computers understand or generate natural language is called natural language processing, or if you want, NLP. And already in the 1950s, researchers were able to translate Russian sentences in English automatically. Back then, the main approach was rule-based, and researchers had to write by hand many rules and many exceptions to these rules. Doing this by hand led to modest results, but it was a recipe for high development cost and high maintenance cost. So little by little, this approach faded away, especially because in the 1980s, 1990s, documents started to be more and more available electronically in digital format. So researchers started to think, ooh, maybe we can use statistical approaches to mine these electronic documents. And this was the beginning of statistical natural language processing. For example, if you had documents in English and the same content in French, then statistical approaches could find interesting patterns such as, oh, how interesting, 95% of the sentences in English that contain the string ABC are translated by sentences in French that contain the string XYZ. The system has no idea what ABC and XYZ refer to. It could be a squirrel, it could be a pair of shoes. All it knows is that statistically speaking, it's very likely that ABC is a translation of XYZ. So that was the main approach, statistical NLP, that lasted for about 2 decades. But there was another drawback to that approach as well, is that we needed annotators to annotate those large quantities of text. So that limited the progress of NLP and was rather expensive. But at the same time, the field of machine learning were working on developing neural networks that were making significant had significant performances in a variety of tasks. So researchers started to think, could we use those neural networks also for natural language processing? Let's take a moment to see what a neural network is. Well, this is a single neuron, not a network yet, a single neuron. It takes as input some numerical information, some values, does some little bit of math, and outputs a single value. So those numbers, 0.8, 0.5, they could represent anything. They could represent an image, for example. And the output might represent, for example, if the image represents a cat, it outputs a 1. If the image does not represent a cat, it outputs a 0, or any value in between. So that's the input, that's the output. But how does the neuron learn? Well, we're going to give to the neuron a whole bunch of examples of input and expected output. And if the neuron gives us the right answer, what we expect, we're going to modify those little weights, because those little weights indicate how important that input is. If the neuron gives us the right answer, we don't modify them. If the neuron gives us the expected answer, if the neuron does not give us the expected answer, we're going to modify them slightly so that next time the answer will be closer to the expected answer. Well, that is a single neuron, not a network yet, but if you connect thousands or millions of such neurons together, you get a very large neural network that can take many, many inputs and output many, many types of output. But the problem with using a neural network for natural language processing is that we have words, we have sentences. How do you fit a word or a sentence into something that requires numbers? We needed to represent those words, those sentences, into numbers. Close your eyes and imagine this sentence: a house with a front yard. What do you see? You see something like that, approximately. Well, we needed to understand, we needed to accept that the neural network's thought would not be an image, but would be a bunch of numbers. And if I use different words, for example, an apartment building with greenery in front, well, you get something very close, different words than my previous sentence, but about the same thought. Well, if we have similar thoughts, we should give the neural network similar numbers. And if I give you a completely different thought, for example, an elephant drinking from a lake, completely different thought, completely different numbers. So that's what we needed. But how do you come up with these numbers? Well, one revolutionary approach was Word2Vec. And by the way, these numbers, we call them embeddings. So one revolutionary approach to come up with these embeddings was Word2Vec. The idea is to have a very small neural network guess the word in between other words. For example, if I tell you, my new blank has a nice front yard. What is the blank? It's any word that refers to a house, a condo, the same, different words, but the same idea. So the network was given words in a sentence and was supposed to guess the missing word. And by training this network with millions of sentences, the embeddings, the words, the numbers, were able to be found automatically, and numbers that for words that are similar in ideas were close to one another, and embeddings of ideas that were different were far away from one another. And the beauty of this approach is that it learned embeddings that that captured syntactic properties, semantic properties, and a little bit of world knowledge. For example, the method figured out that the mathematical relationship between the word Tokyo and Japan, the capital country relationship, the blue line, the mathematical relationship between the embedding of those two words was the same for Tokyo and Japan, Paris and France. So if you told the network the word Italy, it could compute automatically that the capital of Italy was 550, which may mean nothing to you, but for the network, it means Rome. That was a game changer in NLP. Around 2015, the field changed from statistical NLP to neural NLP, where we use neural networks to manipulate languages. And from that point on, scientific advancement accelerated at a very fast pace. Large companies became very active in research and figured out that scale does matter. What does that mean? It means that the larger the neural network, the larger the training data, the longer you train, the more concepts and world knowledge the network learns on its own. They train new models with billions of parameters on the entire internet and develop things like large language models that we know today that can converse and translate in natural language with such high accuracy. But one fundamental question remains. Do these systems actually understand natural language? Well, we definitely need the input of philosophers and cognitive scientists to answer that question. What we do know for sure is that the systems learn that when you ask them ABC, if they answer XYZ, the user will be satisfied. By learning this, they also learned on their own many relationships between words and concepts of our world. But unless these systems are grounded in a real-life setting and can act upon their outputs in this real-life setting, we have no evidence that the models they have built, the internal models they have built, is complete and correct. Therefore, that they understand. But just like my pocket calculator does not understand math, yet is still very useful, even if these systems do not really understand natural language, they are still pretty useful to answer my emails and translate documents.